Okay, we're going to shift gears now and start talking about the quantum numbers. And the quantum numbers are the results of the math from quantum mechanics. And when Bohr and Schrödinger especially started using the wave equations, they got some really interesting results out. And the math that was used for that kind of stuff is like Math 254 stuff here at Mount Hood. All right, it's all stuff that you can do. I used to do it in graduate school, and it's stuff that with modern programs and solve buttons, wow, yeah, pretty awesome. Wish I would have had those then. But anyway, in this class, though, we're not going to talk about the calculus and stuff. We're going to talk about the results of the calculus. And the results of the calculus equations and stuff, we ended up with these four quantum numbers: N, L, M sub L, and M sub S. And they're all relate to electrons and how the energy of electrons works and stuff around the atom. So we'll talk about some of these quantum numbers and their little anomalies and stuff here. This question is a common kind of question in this section that says which one's not a valid set of quantum numbers. So n is literally based back on the Bohr model of n. It's just a whole number. It starts at 1, goes all the way up in whole numbers, up to, in theory, infinity, which is when you extract the electron from the atom. We'll talk about that in lab. L is the angular quantum number. It goes from 0 up to n minus 1. All right? So if n was 3, then L would start at 0, go 0, 1, 2. 3 minus 1 is 2. That would be like the maximum value of L. You will usually have more than one L for every n. All right? Not n equals 1 is the exception, but usually there'll be more than one. M sub L depends on L. So M sub L goes from negative L to positive L. So for example, if L is 1, then M sub L would be negative 1, 0, and plus 1. And 0 is a valid quantum number for this argument. So if you have negative 1, 0, and plus 1, those are three acceptable values of M sub L in that case. When L is 0, M sub L can only be equal 0, but again, that's a valid M sub L, all right? And then finally, M sub S, which isn't part of this problem, but M sub S is only going to be positive or negative 1/2. There's no other values associated with that. So, in this question then, we want to find which one is not a valid set of quantum numbers. So if you go through, I'll go through this one with you, I think. For the first one then, n equals 4, that's a legit n value. N can't be 0, it's not going to be negative or a fraction. So n equals 4 is okay. L can be no bigger than n minus 1. So 4 minus 1 is 3. The maximum value here of L would be 3. So L is certainly not 3 or less, 1, which is fine, so that's a legit thing. And M sub L depends on L. M sub L goes from minus L to positive L in whole numbers. So if L is 1, M sub L can be negative 1, 0, or plus 1. Negative 1 is one of those three numbers. So this is a legitimate set of quantum numbers. There's no problems in that one. Any questions on that? Sweet. So if n equals 6, that's legit. L can't be any bigger than n minus 1, so that would be up to 5, so that's okay. And if L is 5, M sub L will go from negative 5 to positive 5 in whole numbers. M sub L equals 0 is one of the acceptable values here, so this would be a legitimate set of quantum numbers as well. When you get to C, though, that's where the problems start, because if n equals 2, what would be the maximum value of L if n equals 2? 1, that's right. So you can't have L and n be the same. That's one of the big forbidden things, all right? So that is not a legit set of quantum numbers. Now, M sub L minus L to positive L, that would be okay, but you can't have n and L be the same thing. And that's one of the big things to look for. The other thing to look for on these kind of problems is like if you had L equals 2 and M sub L equals minus 3, all right? L, figures out what m sub L can be. And if L was 2, then m sub L can be anywhere between -2 and +2. It couldn't be -3 or +3. That's the other kind of thing you'll often see in these kind of problems. And these right here are okay too. Any questions on these things? Cool. Now, the other part that's really important here is using what's called the NL notation. And up here on the board, I have a little L value and what the letters mean. There's a lot of times energy of an electron depends on N and L. In the Bohr model, it was just N, all right? And that works really well for hydrogen and helium +1, but outside of that, it doesn't work very well. Actual energies depend on N and L. So that's why we use this system here quite a bit. So instead of having an N and an L next to each other, i.e. 31, which would be confusing because is that the N level or what is it? They have a letter that goes along with the different L values. So S means L is 0, P means L is 1, D means L is 2, etc., etc. So in this problem, you can see you've got N equals 3, L equals 1. That means the big number on the outside will be a 3, all right? It's not N equals 4 or N equals 1, which would be those guys. And on this little chart right here, if L equals 1, that means it's a P subshell. So this would be 3P, all right? And that's literally all it is. If you've taken other chemistry courses and you've seen electron configurations like 1s2, 2s2, 2p6, all right? The 1s, 2s, and 2p are NL notations. So you're seeing in this class, hopefully then, how the number is the N, and then the letter itself corresponds with an L value. And that's how we put the electrons in to figure out their energies. Any questions? Okay. Here's a question I'd like you to think about. If an electron subshell has 7 orbitals, what is the L value for this subshell? So see if you can figure out if there's 7 orbitals in a subshell, what's the L value, all right? Now remember, L values can also be correlated here with the letters, but I'm looking for the number here that goes along with L. So see if you can figure this out. There's a couple different ways to do this problem. So Another big part of this section is figuring out how many orbitals there are. And there's different ways to figure out the number of orbitals. But in this particular question, you have 7 orbitals, and you're trying to find the L value. And if you look back in the notes, one of the equations was 2L plus 1 equals the number of orbitals. So what that means is that if you have the subshell L value, 2 times that number plus 1 equals the number of orbitals. So for example, the S subshell has L equals 0. 2 times 0 plus 1 is 1. There was 1s orbital in the S L equals 0 subshell. Now in this problem, we're looking for L. So you can say 2L plus 1 equals 7. So 7 minus 1, 6, divided by 2. That means in this particular case, L equals 3. This is an F subshell. Now, why this works out is if L equals 3, then M sub L, which is the way you figure out the number of orbitals by the number of allowed M sub L's, M sub L, negative L, 0, plus L. So that means negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. And remembering here that 0 is one of the accepted values. It's an orbital. There's 1, 2, 3, 4, 5, 6, 7 M sub L values. So that means 7 M sub L, 7 orbitals. All right? So we would say in this world that the L equals 3 subshell has 7 orbitals or 7 allowed M sub L values associated with it. And it doesn't matter what number is in front, all right, of the F. It can be 4F, 5F, 100F, all right? The F with L equals 3 means there's going to be 7 orbitals inside it. So it's kind of an interesting thing. So one of the things to pull from this problem is that if you have the L value, that the number of orbitals equals 2L plus 1. And you can quickly solve for it that way. Any questions on that? Okay. Now, nodal planes and spherical nodes are a big part of this stuff as well, because in a node, you don't have any wave. And because these waves are electrons, that means there's no electron density. And making a bond with another atom involves like sharing electrons. So if you don't have any electrons to share, you can't make a handshake, all right? There's a quick way to figure out how many nodal planes a system has, and it's based on L. So see if you can use those letters and maybe the little chart up here to figure out how many nodal planes, which one of those will have 2 nodal planes. There you go. to give you a long explanation and then tell you the quick and dirty answer at the end, so bear with me. A nodal plane is like a sheet of glass, and as a sheet of glass goes through the orbital, what you see on the left should equal what's on the right-hand side. And what I've drawn up here real quickly are the S, P, and D orbitals. They're generic look, all right? When they start getting bigger, like D's and then F's, definitely they start having more variations. But more or less, this is kind of what they look like. S is like a sphere, and the P's are like figure eights or infinities, and D is like 2 figure eights. And again, I'm not an artist, as you can tell, so it's pretty cheesy. But anyway, there's no way to split the sphere in half. Like there's no in-between point, all right? So there's no nodal planes when it comes to the S system, all right? You don't have a way to like split it in half. But with the P's, you definitely do. So imagine my sheet of glass goes like right through the middle right there. And you have the same above as below, all right? And it doesn't matter if the P orbital is X, Y, or Z, you're going to be able to take this sheet of glass and put it through. So P has one nodal plane, and the D's right here generally are like these 2 figure eights, all right? So you can imagine I could put like a sheet of glass like right there, and I could put a sheet of glass like right there. So the D's actually have 2 nodal planes associated with them. And even the weird donut one does have 2, although it's harder to see. Now notice here that we went from 0 nodal planes to 1 to 2, and that's the same pattern we saw for the L part up there. So the long way is, yeah, you can draw out what they look like, and you can see that the D's here, answer C, have 2 nodal planes. But the quick and dirty way is just to look at the L value, all right? Because the nodal planes are just equal to L. So in this case, if we have 2 nodal planes, that means we want L equals 2, and L equals 2 is going to be the D subshell. If you were looking, for example, for, well, let's say 4 nodal planes, well, that would be an example of the G subshell, and 0 would be S. So nodal planes just equal L, all right? Another reason why this SPDF thing is kind of helpful, so. Any questions on that? Cool. If you ever, this is, again, a terrible media reference, but there was a movie from like 2001 or so called 13 Ghosts, which was a remake of a movie from the 60s, long story short. But anyway, there's a scene where this evil lawyer just sliced right through with glass, but it's really gory and not appropriate for my more G-rated than not Chem 221 lecture. But if you do see it and you're a fan of horror, then I do recommend it. But anyway, planar nodes are one type of node in these systems, all right? And again, they're like sheets of glass, and that means you couldn't make a bond right in the middle. You could make a bond here or there on the p orbital, but you can't make it in the middle. But there's another kind of node called a spherical node. And this question says, which of the following orbitals has 2 spherical nodes? Now, the planar nodes just equaled L. Spherical nodes, the equation, if you saw on the last slide, n minus L minus 1. So see if you can figure out which of these combinations, these NL combinations, once again, n minus L minus 1 equals 2, all right? Only one of them does. Here's the L values that go along with the letters. See if you can figure it out. Okay, so let's say you wanted to figure out the number of spherical nodes for a 1s orbital, all right? What is the n value for 1s? 1, good. What is the L value for an S subshell? 0, that's right. So for this one, you'd go 1 minus 0 minus 1. There's no spherical nodes for the 1s subshell. All right? So we're taking the number, that goes right there. S up here means L equals 0, so that's where that 0 is. N minus L minus 1, no spherical nodes for 1s. Is that cool where that came from? All right. So going along, 2p, n is 2. P means L is 1. Minus 1, no spherical nodes. 3D. N now is 3. D means L is 2. And we're going to still subtract 1. Striking out. 3p. 3n minus 1 for p. Minus 1 for 1 more. 3 minus 1 minus 1. 1 spherical node. So if you, wait a minute, did I do that? No, wait, 3n minus, wait a minute, uh-oh. So let's see, 3 minus 1 minus 1. Oh, darn it. Oh, wait, yes, 1 spherical, okay. Sorry, I'm still coming back from Thanksgiving, gang. All right, sorry. 1 spherical node. We want 2 spherical nodes. I was like, oh crap! I thought they were all 0. So anyway, prof had bad spaz. Prof had back on. So yeah, 1 spherical node. Okay, and then you can see in this one, oh boy, 4 minus L, which is 1, like it was before. 4 minus 1 would be 2 spherical nodes. Sorry, I kind of spazzed that explanation. But hopefully you get an idea then how this works and stuff. We were looking for 2 spherical nodes, and I got excited because there was 1 spherical node there. But anyway, so this would be the example. So 4p would be the best one. Now, if the other ones were sheets of glass, these are like balls within balls. That's the easiest way I can use to think about it. So if you have like a big s orbital, a spherical node would be like a second ball inside, and on that second ball inside the bigger ball, there would be no electron density. And this can be important when it comes to bonding. The p orbitals and d orbitals will also have them. They're like gaps in the p orbitals, and I showed some pictures in chapter 6 part 1 towards the end if you're curious. Any questions on that? Juliet? Oh no, that's okay. I was just I never read body language very well, and with our masks on I can't read anything, but I had to double check. So all right, prop out back on. Let's get out of that problem. Okay, so now that you know all these NL, spherical nodes, blah blah blah, now it's time we can start figuring out electron configurations, all right? And what I'd like you to do is try and figure out the electron configuration of neutral chlorine, all right? And I would absolutely use the periodic table if you want. See if that all works out. right, so I have lots of scribbling on the board that may or may not be helpful, and hopefully it's stuff you've seen already. But when you start to figure out electron configurations, this goes back to what's called the N plus L rule. And again, in Bohr, what he saw in his model, that 1, 2, 3, 4, 5, we talked at the beginning of lecture today, he saw that the energy of electrons was only based on N. And that works really awesome if you have single electron atoms. So for example, hydrogen, it works well, and also helium plus 1. But when you get to helium itself, neutral, or carbon, or oxygen, or uranium, then it's no longer all about N, it's about N plus L. And the N plus L rule is what we talk about when we talk about how electrons get put around atoms. And this right here in the lower right here is called an Aufbau diagram. And it's one way that you can actually figure out how these electrons get put in. And to draw an Aufbau diagram, you start with 1s, and then everything above it is just an s with a bigger number. So 1s, 2s, 3s, 4s, etc., etc. You skip one and go over to the next subshell letter, which is p. That's a 2p, all right? So 2p, 3p, 4p, 5p, etc. Then you skip another one and you go to the next letter, which is d, 3d, 4d, 5d, and you can skip one and go to f's, 4f, 5f, 6f. You can skip one and go to 5g, which would be right there, etc., etc. Anyway, once you get as many of these as you need, then you put these diagonal arrows in, and this is the order that you put electrons in. So 1s will always be first, and the next arrow, 2s, will always be next, then 2p and 3s, 3p, 4s, 3d is after 4s, note that. These are N plus L lines, so like N plus L, 1 plus 0, 1, etc., etc. The punchline of the Aufbau diagram is that s orbitals can always hold up to 2 electrons. They can be underfilled, but they will never have more than 2. P's will always hold up to 6, never more than 6, but less than 6 is okay. D's will hold 10, F's will hold 14, the G would hold 18. Lots of patterns, all right? 2, 6, 10, 14, 18, etc., etc., all right? So if you have a problem like this, chlorine, you need to know how many electrons it has. And how do we find out how many electrons neutral chlorine would have? Yeah, periodic table, right, the answer to basically everything. And in this class anyway. And chlorine there is number 17, all right? So that means chlorine has 17 electrons. So one way to do this then is you could literally just start with 1s here on the Aufbau. And remember, s's can hold up to 2 electrons. Less is okay, but not more. So 1s2 would be the first part of this, all right? The superscript represents the number of electrons. The number 1 right there represents the n. And the s again represents the l. So 1s2 would be the first step. So that's 2 of my 17 electrons. We have 15 more to go. Woo-hoo! So the next one on the list, we've finished up that arrow. The next one would be 2s. That also holds 2 electrons, just like the 1s, but no more than 2 electrons, all right? So we're shut down there. We'll go to the next arrow. 2p is first. And p's always hold up to 6 electrons. So that would be 2p6. And oh my gosh, I've forgotten how many electrons I added. No problem. Add up the superscripts. So 2 plus 2 plus 6 is 10. I put in 10 of my 17 electrons on chlorine that I need. So I'm not quite done yet. Then I'll go to 3s. 3 s's, like the other s's, hold 2. Now I'm over here at 3p, that's the next part. Now remember, p's can hold up to 6, but in this case I have 2, 2, 6, 10 plus 2, 12. I have 17 electrons total in chlorine. You can have less than 6. So for chlorine here, I would write 1s2, 2s2, 2p6, 3s2, 3p5. And that If you count up all those superscripts, that gives you the 17 that chlorine has if you look on the periodic table. Always follow this order. So you're going to write 1s2 a lot, 2s2, etc., etc. I made a note right here. You could also use what's called noble gas notation, and that's fantastic too. 1s2, 2s2, 2p6 is the neon core. And if you want to use noble gas notation, you put the name, the symbol for the noble gas in square brackets. So calling it neon in square brackets 3s2, 3p5 would be fine too. You always have to go backwards. Like you can't have like argon -1, which would be nice, a lot less writing, but you have to go backwards. Any questions on that? Now, sometimes people love using Aufbau, and that's cool. If you love using it, keep using it. Honestly, that's kind of what I use. However, I've had people do this different ways too, and there's nothing bad about any of these methods. One thing you can literally do is just in your calculator, memorize, whatever, just put in the order and go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. I've seen people do this in their calculators, and that's fine. And you just follow that order until you run out of electrons, basically, and then you stop. There's nothing wrong with doing that if the Aufbau is weird. Another way that you can do this is to what I call read the periodic table, and that's another little silly picture I have right there. The S block elements are groups 1A and 2A and helium. All right, helium really should be above beryllium for this conversation, but for noble gas reasons, it's over there. And the number on the left, the period number, equals the end number. So for example, down here at francium, this would be a 7s1. Everything in this column has an S1 on it. And the number that goes before it is just this number right here. So a really cheesy way to figure out francium is you go backwards to the noble gas, radon, so put Rn in square brackets, and write 7s1, and you'd be good to go, all right? It's a very quick way to do things. So these two are the S block, and you just read the number. The right-hand side, the 6 columns, not helium again, helium goes right there, but these guys are called the P block. And you can do the same thing with those. So for example, radon right there is in the 6th period. This would be a 6p6. 1, 2, 3, 4, 5, 6 is what we were doing just a second ago. All right? So on the far right, that would be a p6 column. And you can read the P also just based on that part right there. Now, the D's for different reasons are the period number -1. So fascist D orbitals, I know. Scandium would be a 4 - 1 3D orbital. That would be 3D1, 3D2. The actinides and lanthanides down here, which start right here, they're the period number -2. So you can see that there's a gap right here, 57, all right? So lanthanum arguably is 6 - 2, 4. This would be the beginning of the 4F orbitals. This would be the 5F down there. So sometimes people like reading the periodic table, and that's awesome. And again, the S's have 2s, the P's have 6, the D's have 10, et cetera, so you can kind of figure out where you are. These are all possibilities, and whichever one you want to use is totally cool with me. Yeah?
What's the maximum electron that the Aufbau diagram for D and P?
Good call. The S's can hold up to 2, the P's can hold up to 6, D's can hold up to 10, and F's can hold up to 14. Good. And G's then would be 18 after that band and stuff. Good. Any questions? All right. So here's another kind of problem you might see. All right, what neutral element has this electron configuration? And there's a couple different ways to do these kind of problems. See if you can figure out which element it is. And it's a neutral atom. We'll talk about that later too. relatively easy way to do this problem is because it's a neutral atom, all right, you can just literally add the superscripts together because the superscripts will tell you the total number of electrons. Total electrons equals atomic number from the periodic table, et cetera, et cetera. So 2 plus 2 plus 6 is 10, plus 2 plus 6 more, that would be 18. 18 plus 10, 28, plus 2 would be 30. And if you look on the periodic table, number 30 right there is zinc. Now, I put this problem up for a reason though. If you looked at just the last 2 electrons, which is often something you can do, all right, 4s2 on the periodic table, here's 4. These are the s blocks. 4s2 looks kind of like calcium. So notice in the way that this was written, 3D was put inside. The order that we fill the electrons in, 3D would be the outside. So let me point out here in the Hofstadter diagram what that means. 1s is always first, then 2s, then 2p, then 3s, then 3p. But before you start doing 3D, you should fill 4s in first and then go to 3D. So if we were writing the electron configuration out, you'd probably go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 would be there, and 3d10 would be at the end. The 4s2, 3d10 is an electron filling order. This type of way, where the 3D is put inside there, is really helpful when you're making ions. And I'm just throwing this out there, not to be mean, but just to say you're going to see both types out there. Sometimes when you're filling in the electrons, 3d10 would be on the outside and 4s2 would be on the inside. But we're going to see here in a little bit that zinc, when it makes zinc plus 2, the 4s electrons are the ones that come out. So sometimes you'll see it listed like this. Sometimes you'll see 3p6, 4s2, 3d10. You'll see it listed both ways. And I apologize as your instructor. It's just one of the things that happens in this area. Any questions on that? Okay. So again, always remember you can always add up the superscripts and stuff to figure out where you are. Okay. Neutral tin, all right, is an element and stuff that you can figure out the electron configuration for. The symbol for tin is Sn. See if you can figure out which of these would be the correct electron configuration for tin. are several ways to answer this question. But what I would do definitely is start on the periodic table, all right? And 10, if you go backwards to the nearest noble gas, because all of these are electron configurations with noble gases. If you go backwards from 10, the last noble gas would be krypton, all right? So right away, well, there's only one of them with krypton, so that's pretty chill. Now, that would be the one way to do it. So you can say, hey, the last noble gas is krypton. That should be the answer. And to be honest, it is. Now, another thing you could do is 10 right there, number 50, is in the P block, these 6 columns on the right. And P's, like the S's, you can use these numbers directly to figure out what it is. So indium right there would be a 5P1, and 10 right there would be a 5P2, all right? And a couple of these have 5P2s, but xenon has more electrons in it. It's past 10, so it wouldn't be xenon. It's going to be krypton for the noble gas. So for all of these reasons and stuff like that, then it has to be answer C, all right? The nearest noble gas was krypton. When you go backwards, not forwards, but you have to go backwards. 5s2, 4d10, 5p2. But again, if you can read the periodic table, that makes it even easier. This is kind of a funny thing I should point out. If you see some kind of 3 symbols like that, those mean that those are some of the the elements that haven't been officially recognized yet. And in the old days, a lot of them down here did. And number 118, which was right there under radon, was listed as UUO. And the UUO is just a way that they used it. The first U means 100, the next U means 10, and the O means 8. I don't remember the rules off the top of my head. But anyway, now it has an official symbol, which is OG, but it's 118 electrons, so there's no way that it's going to be 10. Chemistry humor is a little dry sometimes, all right, I won't deny it. But anyway, any questions on how you could find 10? This system is the orbital box notation. And orbital box notation is really helpful when it comes to the magnetism, which we're going to get into a little bit later. But see if you can figure out which neutral element has this electron configuration. So again, similar to what we did before, but a little bit different too because of the orbital box notation. Boxes themselves come again from the number of allowed Emsebel values. So let's step back to the quantum numbers just real fast. If you have any kind of P system, 2P, 3P, 4P, etc., P means, once again, that L equals 1. And when L equals 1, Emsebel goes from negative L to positive L. So that would be negative 1, 0, and plus 1. 3 allowed Emsebel values means 3 orbitals. So when you draw three boxes like that, one of them would be m sub l is -1, one of them would be m sub l equals 0, and one of them would be m sub l equals +1. I see I wrote 2 right there when it should be a 3, but it's the same idea. Whatever the number is in front of the p, it's going to be that one. Likewise, when you write s, S means L equals 0, and the only value of m sub L is 0. So that's one orbital, one box. All right? So we'll always write one box for the S's. We'll always write 3 boxes for the P's. We'll always write 5 boxes for the D's, etc., etc. And when you fill in the electrons, we haven't talked about it too much yet, but m sub S, positive or negative 1/2, means with the magnetic field or opposite the magnetic field. That means you can have one up arrow and one down arrow per box, per orbital, all right? So this is why S's always have 2 electrons, I was talking about earlier. And the P's, because there are 3 boxes, 2 electrons per box, P's will always have up to 6 electrons, etc., etc. Questions on any of that? Okay, so for this problem then, we're looking for something that is neon 3s2, 3p4. All right, that's what that means right there. Well, 3p, go to 3, p start over here. Aluminum would be 3p1, silicon 3p2, 3p3, 3p4 should be sulfur. All right, so once you see that then, it's pretty chill. Any questions on that? I have lots of JQ element symbols in some of these, and that's another stupid chemistry joke. I've told some of you this, I think, before, but there are no J's or Q's on the periodic table. So one day if you get to name an element, use J and or Q, please. So I use JQ sometimes. It's just something that doesn't make any sense. I need to get a life. Okay, let's take a break. This is a good place to take a break. It's about 10:54, so about 11 or so, we'll come back and knock the rest of these out. So.